in the last class we saw these hard problems which will be typical in this course. So TSP, subset sum, integer programming. These optimization problems are difficult to solve. They have not been solved yet in efficient or in deterministic polynomial time. There are no practical algorithms, but if a solution is given, then it can be checked, it can be verified. Right. So that inspired us to define NP by verification protocol or verifier Turing machine given a certificate, and we showed that NP is in exponential time and contains polynomial time algorithms. It's in the middle. So now to make more sense, or at least to redefine NP in a different way, we will discuss non-deterministic Turing machines, where in every step there are two possibilities to move. Okay, the transition function is actually a relation. So we simplify it by saying that there are two transition functions, delta 0, delta 1, and machine can take any of these. We do not know what choice it will make, but we say that M accepts a string if there is some accepting path, and it does not it rejects input if there is no accepting path, right. All the paths reject, but number of accepting paths, remember, for t steps the number of paths is 2 raised to t, so it is exponential in the time, right. So this really you cannot implement it efficiently in practice. This is a theoretical construct, NDTM. So time taken by M on X is defined as the maximum over all the possible paths. Okay, so what is the longest path which leads to halt? That is the time taken. So and this is important because to decide whether it's an X is a no string, you have to go over all the paths. So in particular, none of the paths should be infinite. Okay, every path should be finite, and amongst those, what is the maximum? That's the time. So as I've already said, NDTMs are much more abstract than the Turing machines. So in particular, we cannot identify with a physical device. Right, a physical device like a computer or even quantum computer, we can't really identify NDTM with those because it is kind of checking all the paths, and there are exponentially many paths. So there is no way to efficiently map this to a physical device. I mean, if you try to map it to a physical device, then the time becomes exponential. It becomes a bad algorithm. Okay. So NDTMs motivate the following class, complexity class. Analogous to Ntime. And this will be called Ntime, T of n. So those languages or decision problems that are decided by NDTM in this much time. When NDTM M in time big O of Tn. Right. So it's the same definition as D time, except now you are using NDTM instead of Tm, and the time is around T of n. So all the paths, they are of length around T of n, and the Turing machine is essentially going over all the paths and checking whether all of them reject some input string x. So it is not in L, and x is put in L if x is in L if and only if one of the paths accepts, is an accepting path in this NDTM computation. And the theorem is, what is this n time now to do with NP, right? That's the question, and it's actually another characterization of NP. So if you take the union over all these problems which are solvable in non-deterministic polynomial time, then the union is exactly NP. Okay, so what this is saying again is, any problem which is efficiently verifiable has a fast NDTM, and any NDTM, fast NDTM, any problem that is being solved by fast NDTM, it has it is easy to verify. Okay, so that's what we'll do in the proof. So let L be in NP, which means there is a verifier, Turing machine M, and the setting so X is a yes string if and only if there is a certificate which is not too big, just slightly bigger than the size of the input X, on which the verifier accepts. That is the definition of NP via verification, via verifier. And how do you put it in n time? So you can think of now this verifier M as a NDTM which doesn't know the certificate. U, it just tries to guess it. Okay, so in every step, whenever U is needed, it just guesses that bit of U. The guess will be either 0 or 1, and that makes M an NDTM. Okay, this is the simple idea. So define NDTM N as on input X. So N will be, so in the first x to the c many transitions or steps, delta 0 writes a 0, and respectively delta 1 writes a 1 on the tape, right, on the work tape. So by either picking delta 0 or delta 1, 0 1 string has been written, which is of length x to the c. This is the initial part of computation of n on input x, and then it will use this string as a certificate u. Okay, it will pretend as if this is a certificate, and it will do the computation of x comma u based on m. So, in the first these many steps, delta 0, delta 1 writes on the work tape, and moves right. So, after n has written, this x to the c bit string w, it simulates m on x w. Okay, so now simulation happens, and whatever is the result, it is outputted by n as the answer. So, clearly, if x is in L, then at a certificate W, n will accept, otherwise n rejects. For all W, guessed, right, because there is no certificate. So, whatever guess n is making in the beginning initial part, it will fail, and m will keep rejecting x comma w. That was guaranteed by definition of L in NP. So, this means that we have shown L to be solvable by a non-deterministic, by an NDTM in how much time? So, initially there was this n to the c many steps to guess w, and then on that it was n to the d time. Where n to the d time is for simulating m on xw, right. So, that finishes the part that NP is contained in union of n time. NP is contained in some n time, n to the c. So, now the converse. Converse means that we will take L in n time n to the c and show that L is in NP. So, conversely, let L be in n time n to the c prime with the NDTM n of time complexity less than n to the c. Okay, so remember time complexity is around n to the c prime, right. So, instead of saying around n to the c prime, I am just fixing it to be n to the c, something just smaller than n to the c. So, that is the time complexity for an NDTM to solve this language L. Now, you want to show L in NP, right. So, you have to give a verifying Turing machine, a Turing machine that can verify certificate. So, that Turing machine will actually be just n. And what is the certificate? The certificate is which path to take what choices to make delta 0, delta 1 in the steps so that it accepts given input. So, define verifier Turing machine M that on input X and string U does what? Just what N does. So, simulate N on X using the transition given by U for each step. Right. So, N will require this information what choice to make, because it is an NDTM. Those choices will be given by U, or U will be used for those choices, and so that makes N a deterministic Turing machine. It is fast, and if there is a way for N to accept, if there is a certificate U, then it will accept. So, this means that L is in fact in NP. Right. So, ultimately what we have shown all together that NP is equal to union of N time N to the C. Right. That is what we started with in the claim. So, every problem in NP is in some N time N to the C, every problem in N time to N to the C is in NP. Right. So, which means that NDTM is a perfect way to characterize problems that are easy to verify and maybe hard to solve. Right. All these examples we saw, they were quite hard. Okay. So that completes definition of NP and the discussion vis-a-vis NDTMs. Now let us focus on a single problem in NP, which is very important, and that is called satisfiability. So now we present a problem that is the hardest in all of NP. Okay, so we will focus on one problem that actually every problem in NP reduces to. So, if you solve this one problem, it is called SAT, then you will solve all the other problems in NP, and by solving I of course mean practical algorithm, okay, and formally deterministic polynomial time algorithm. So, in the course overview we have discussed this. Let us now formalize. It is called SAT. It contains Boolean formulas. Phi is a Boolean formula in CNF. CNF is conjunctive normal form, so it is basically AND of clauses, where each clause is an OR of variables, and the variables can be either the original one like X or negation of that negation x, not x. So they are called literals. So it's a conjunction of disjunction of literal. So the key thing here is satisfiable. Phi is a satisfiable Boolean formula in CNF, and the CNF is conjunction of disjunction of literals. Okay, it's conjunctive normal form it is called. So that is formula phi actually is given by, so in fact let me also mention the variables. It is given as and of, or of, literals or variables, Vij's, where this Vij is in x1 to xn or their negations. So, and this is called a literal. Okay, and this is a CNF formula, and this thing in bracket or of Vij's, this is called a clause. So it's a conjunction of clauses. And let's see a simple example. Okay, let me also mention what is satisfiability if you have forgotten. So phi is called satisfiable if there is an x in 0, 1 star or n variables. So n 0, 1 values, you can also think of it as false true, such that phi on x is 1. Okay, so satisfiable just means that the formula becomes 1 or formula becomes true. If this happens, then we say that phi is satisfiable, otherwise it is unsatisfiable, or you can also say that otherwise phi is false. Okay, it is just a contradiction. So for example, x1 or x1 bar x2 bar, let's say, this clause with the second clause x1 bar. Okay, this is it satisfiable or not? So you have to set x1 to be false, otherwise second clause will not be true. And even after setting it false, the first clause you can set x2 to false and first clause becomes true. So this is actually satisfiable, it's in SAT. While if you take x1 and x1 complement, now whether you try 1 or 0, one of the clauses will remain 0 and it's a conjunction, so you will get 0. So this is not satisfiable, and you can see clearly why, because it actually hides a contradiction. It's saying x1 is true and also its complement is true, and this is indeed the only way to have an unsatisfiable formula. There is a contradiction inside. So first lemma we show, easy observation about SAT, is that SAT is in NP. Why? Because given a formula and an assignment, you can check whether it's satisfying or not. So accept formula phi if and only if there exists an x such that phi x is 1. So that is what the verifier will do. And if you want, you can think of this as U also. That's the certificate. So this is easy to verify by Turing machine. And this is the certificate. Right. So basically the certificate and the verifier, certificate is just the assignment, alleged assignment, and verifier is just the one that algorithm that will substitute in phi and evaluate the value. Since this is just a formula, you can easily calculate the value by a Turing machine, by an algorithm. So now comes the hardness part, right? So this is saying that SAT has a verifier and hence it also has an NDTM. But we'll now prove something much stronger. We'll show that every problem in NP can be reduced to SAT. So let L be an NP problem, then L can be reduced to SAT in deterministic polytime, which means that there exists a polytime reduction algorithm, let's say Turing machine N, such that for all inputs x is in L if and only if nx is in SAT. Right, so that's the reduction. N is the Turing machine that reduces original input, which was you wanted to check whether it's a yes string of L. N will transform that string, but efficiently, into another string, and that will become a Boolean formula, which is satisfiable if and only if x was a yes string. Okay, so what lemma 2 is claiming is that this N exists. We have to build this algorithm that can transform any input of a easy to verifiable problem L into a Boolean formula. Right? How will you do that? That seems impossible. How do you convert arbitrary inputs to Boolean formulas? Like suppose you were given a graph or a number. How do you convert it into these and or not gates? So the way we will do this is we'll use the verifier of L. That's the idea. The idea is express the verifier algorithm verifier Turing machine steps as a Boolean formula. Okay, so this will be a translation. It will translate every step into, let's say, a clause, and then whole accepting path will be converted into a Boolean formula. So the Boolean formula being satisfiable will actually mean that there is a certificate that existed for X in L. Okay, so the when you are translating steps into Boolean formula, the unknown values are these guesses, the freedom that NDTM had or the verifying algorithm needed, the U, right, the certificate. So if it exists, then the computation, there will be an accepting path. If it doesn't exist, all paths are rejecting. That's the idea. So let's do that. Let's implement this idea. So as L is in NP, there exists a polytime Turing machine M, which we keep calling verifier, such that X is a yes string if and only if there is a certificate that M accepts. Let M on XU is 1. So say M takes less than T steps to halt. So T is the time complexity that we are talking about. M is the again verifier, U is the certificate, T is the time complexity, and L was your original problem, which means that there are T max at most T configurations are there for the Turing machine execution. So with each configuration, C, we associate a bunch of variables right. So configuration is has to store everything there is. It's a snapshot of the Turing machine execution, right? So in particular, what is the state? What is there on the input? Where is the input tape head? Where is the work tape head? What is the work tape string? Yeah, so that exactly defines a configuration. So let us write that. So the bunch of variables is state, head position of the two tapes. P prime and P are basically pointers where the head is. What is there on the input tape? And what is there on the work tape? So this is the state variable. This is the head position. On input tape. Head position on work tape. That's P of C. This is the input tape string. Remember, this input tape it is infinite, but it has only finitely many filled cells, right? The others are blank. So blank we don't care. And this is the work tape string. Right, so that is a configuration, and these values will keep changing step by step. But it will use the transition function. So we have to encode whether every step is correct. It is following the transition function. So final formula for the execution of the verifier M on input x comma u looks like the start configuration C1 should look as the definition of Turing machine demands. Then a computation sequence of steps from configuration C1 to C2. So this will break further. I'm just only giving the top view for now, and then stop with configuration C2, accepting x comma u, right? Accept configuration. So now let us look at the details.